So today I would like to present you our paper, which was published in Models Conference last year on architectural design decisions in the fourth industrial revolution. So we conducted a literature review and we developed a taxonomy. So in the next 20 minutes, I would like to talk about that. So besides me, also Kirill, Dorofeev, and Sebastian Voss were involved in this paper. So we are working, or used to work, because some of them left in the meantime, but we are part of Fortis Research Institute in Bayern with a focus on software-intensive systems. So that's the major focus of the institute. So first, I would like to explain what we understand with our architectural design decisions. So here we see one example from Basis 4.2 research projects. So in this research project, we have several demonstrators, but one of them is this simulation of the flexible manufacturing line. So we here have different components from different companies, from industrial partners. And for the presentation purpose, I will just focus on the one small part of this demonstrator. So this is this working station, which is shown here. And so to explain the process, the can, so the product is coming to the through the conveyor, then the pick and place station 2 will pick the can and put it on the turntable. Turntable will turn and move it to the first working station, which will insert the cover. Then it will move further to the second working station, which will insert the screw, and then the last working station will do the screwing process. And then the pick and place tree will take the can and move it further in this manufacturing line. So this part, we consider that as a small plant, as a small factory. Exactly, those are the components that I mentioned already. So we have different domain models here. The main models which describe different aspects of the manufacturing process. So first is the topology. So we see the stations that are involved. So the position of the stations, also the hierarchical relationship. For example, pick and place station contains horizontal axis, vertical axis, and gripper as a component. And we also have for each station also a description what can this station do. So this is usually done with ontologies, but so here we just simple and abstract. For example, this station can do screw and press steps or functionalities. And then also products are described by recipes. So this is the production. Our recipe contains production steps which need to be done in order to produce the product. So we see here some examples, very simple, and later on we will see some application or methodology which can be used to model those recipes. So here we see different recipes, and they're described they have different production steps, maybe some internal constraints. And then we come to the first design decision. So this is production planning. So we are producing product A, and we have a software components, and we have stations that are running this, that are performing those steps. And now in the meantime, we got a new product which was not planned in the beginning, and now we have a new production step, and we have to decide where this production step should be performed. So on which station. And we see that we already have those two steps already allocated to those two stations, but we have now to decide where should we allocate the pressing step. And we have some candidates there. So those 4 components can do this. So they have those capabilities. But now then we consider also the precedence in the precedence order in the recipes, also the topology order, and some other constraints, for example, memory capacity of the controllers, or maybe utilization factors, and so on. And then we decide where this which station will perform this step. So this is one example, one decision. Now we have also service composition. This is also, I will not speak too much about it, but so we have an orchestrator which is invoking atomic production services. And because we have different requirements, we may be forced to do composition. So to take part of this orchestration and to move it near the process, near to the PLC, to execute it on the PLC. So we have a composite small orchestrator which is distributed to some PLCs. So this is service composition, second decision. And then deployment, which is clear. So as in other domains, so we have software components, which are usually function blocks in this domain. And the question is how to deploy them, how to distribute them to the controllers, PLCs in this domain. And there we decide, okay, we also consider different constraints, different optimization criteria. Also execution semantic is very important here. And then we decide where each function block should be deployed to. So this is the third. So those are like 3 examples that are relevant for this domain, but there are also some others that I will show you. So this is what we consider with architectural design decisions. And now what we have in Industry 3.0, so in the current state, is that we calculate those decisions, or we derive them once at the design time, and then we have a running system for maybe 20 or 30 years. So ideally we don't have to change anything. So maybe calculating those decisions is time consuming and requests a lot of engineering effort, but it's done once, and yeah, we are then fine for many years. But in Industry 4.0, we have a goal to have a flexible production, so flexible and optimized production. So it's possible to change production very frequently, to produce a new product, or to minimize the downtime. So those decisions now have to be done more frequently, and that's why we have to find a solution to reduce this effort and time to conduct them, but also to reduce errors. And of course, automatization of those decisions is something what we need, and this is also done in other domains. For example, deployment. There are a lot of works in this direction, like automatizing the deployment calculations. For example, in automotive domain. But this brings us to the need for this work. So what we need, because we have a lot of solutions from other domains, and we have this quite huge area. So we need an overview for architecture synthesis and optimization in Industry 4.0, and this overview would classify existing approaches. So it will offer user or practitioner a possibility to compare possibilities and to choose the appropriate one for its use case. But also we can use this overview for as a common ground, because what we face in different research projects is that we use different terms for different decisions. For example, production planning is also called service composition or task assignment. So there is a misunderstanding between different projects and different research works. So it would be nice to have like a common ground for this. And last but not least is the possibility for the young researcher and PhD students to. So this overview would maybe make easier to find research work, and also to position own research work, so in which area it belongs. So that's why we provide a literature review and taxonomy on architecture synthesis and industrial and optimization in Industry 4.0. Exactly. So I already mentioned what we did. So we want to also identify research trends and the research gaps, which is also something that we get from this work. We also want to communicate better our ideas and terminologies when we speak about architecture synthesis, and also to understand and this better. So sure, just about methodology. So we conducted literature review and developed taxonomy. So on the right side, we see the workflow. We base our work on the work from Nickerson et al. So we first defined topic, of course, and formulated the research questions, and then iteratively we developed taxonomy, and we reviewed papers and classified the papers. We deduced the dimensions and characteristics of taxonomy based on our experience in different research projects, but also based on the findings that we got from the research papers that we analyzed. Exactly, and then in the end, when the taxonomy was over, then we try to find to create some charts and to see if there are some findings, relevant findings for us. So this now we will see a big picture of the taxonomy. So what we notice is that architectural synthesis and optimization in Industry 4.0 revolves around 3 major topics, which each of them evolving in sub taxonomy, so to say. So architectural synthesis and optimization needs architectural models as an input to derive different decisions, and this synthesis is done as a part of design space exploration. So we derive the different design decisions, and we use different optimization tools to do this. So we use different solving techniques, but also we apply different constraints and objectives. So this is done. This is shown also here quickly. And now I will show each of these taxonomy a little bit more. So first is I speak about the architectural models. This is the first major topic in this taxonomy, and I will explain this taxonomy based on the I will describe a plant, and then I will try to explain what each dimension means. So so we see here the plant on the upper part in the blue, and below are the are architectural models that we can use to describe different parts of the plant, and also some implementation models below. So we have a 5 different major dimensions. So first we have a topology. Topology describes plant. So plant or factory contains different resources, production resources or transport resources. They are usually stations, but it can be also a human worker, for example. And plant is described by topology. So so the topology describes what is the position of the stations, what is the hierarchical relationship. And what we see here is the application of domain-specific languages or modeling approaches like automation ML, but also our PNID. That's something which is very domain-specific, but also the application of the generic directed graph to describe topology of the plant. Production resources, they contain atomic or composite capabilities. So capabilities are semantic description of effects that the resource is able to achieve. So what can each resource do, like pressing and screwing, and those capabilities or the capability descriptions are the major part of the resource model, and we usually meet application of different ontologies to describe that. So it's quite then easy to do reasoning and to do matching between capabilities, but also automation ML or some other languages are also applicable as well. Stations are controlled by PLCs controller, and they are described by a hardware architecture. And what we see here is the most often is the application of domain-specific IEC 64099 and IEC 61131 standards. So they have so-called device model and configuration to describe hardware architecture. So to describe PLCs, connections between them, memory capacities, and so on. And also those PLCs are running one or several control applications, and they are described by software architectures. And besides, of course, UML or ADL, we also have here a domain-specific application model and so-called program from those two standards. So they are the most frequent one. And those applications can be then expressed also as the production services, which are then invoked by orchestrator that produces a product, that executes a recipe, which describes the product. And here we have also application of generic UML activity diagrams, for example, but also BPMN, business process modeling notation. Some domain-specific languages are also applicable here, or we met them in the research papers, and some domain-specific like sequential functional chart from the 61131 standard. Exactly. Second major dimension is are those design decisions as a part of the design space exploration. So we have here 3 major dimensions: design decisions, decision multiplicity, and search incrementality. So here we try to list all decisions that are common in this domain. So first of them is deployment, as I already mentioned. So allocation of function blocks to PLCs, like a pure deployment decision. But there is also possibility to think about allocating skills or services to the station. Then scheduling, like function block scheduling, so calculating execution order of function blocks, or communication scheduling, so temporal order of communication. And we have also production scheduling, so to decide when which product will be produced. Then third decision or third group is hardware platform synthesis. So this is like decision which PLC will control which station. Do we have redundancy there? Is one PLC controlling several stations because it's capable to do this as hardware resources to do this. Then service composition, as I already mentioned. So here we distinguish between orchestration. So we have an orchestration application which is invoking atomic or composite services, and choreography, which doesn't have this standalone application. So each service will invoke a subsequent service after completing its operation. And of course, we, as a part of service composition, we can think about extracting services from monolithic applications and doing that also opposite, like doing decomposition. Part of the service composition decision is also service matching. So matching required services which we derive from product recipes with the offered services from stations, from resources. And also, second possibility is to do, as a part of matching decision, is to do capability matching. So usually with ontologies, to see what can we find a list of the capabilities that are able to fulfill to perform this production step that we need. And last decision here listed is production planning, also contains matching as a subtask, and the main part of the production planning is to allocate resources to the production steps. We distinguish also if the works did just one decision, so just calculate the deployment, or if they did also multiple decisions. So if they calculate the deployment and scheduling, and if they did it like sequentially, or they do it as a single joint problem. And also the search differences, if the works did like monolithic search, like everything, they search the whole design space, or if they divided the design space, so they did compositional search. And third option is incremental. So if when we have a change, we are trying not to search the whole design space, but just try to identify the part which was affected, and then to search this part. And last the dimensions, I will a little bit speed up, is about optimization tools. So it's also quite aligned with some other works from software engineering domain. So here we have 4 major dimensions: solving techniques that we try to classify, then constraints that are applicable here, objectives or optimization goals, and the dimensionality of the optimization. So I'm not go deep into this. So you can see also in the paper like what is how they are like classified further. There are several, quite complex, but also not. So I will now talk about some findings that we found analyzing the papers, and after we classified them in the taxonomies. So first we tried to see, okay, what are the papers are doing regarding decisions, design decisions. So the most of the papers are doing single decision synthesis, and if they do multiple, then those are usually sequential. Then from those multiple decisions, we usually see that deployment is done together with scheduling, which was also to expect, and also production planning, as I mentioned, is done together with matching, as I already mentioned. When we speak about search dimension, there's very few incremental approaches, and the most of them are monolithic. So maybe one search direction, future research direction, will be maybe to investigate incremental or monolithic search for multiple dimensional problems. So because in Industry 4.0 we speak all the time about frequent changes, zero downtime, and optimized production. So maybe this incremental and compositional search would be something which is worth investigating for the Industry 4.0 problems. This slide shows alluvial diagram for collating design decisions, architecture, and models. So just shortly, what we can see here is that you usually use hardware and software architecture for deployment and scheduling problems, and the products and the resources models for production planning and matching, for example. And we see application of different modeling approaches here. Formal modeling is quite often. Also, we have a lot of application of ontologies and directed graphs, but also domain-specific ones are also quite common as well, especially those with IEC 64099, and they are mostly used for modeling software and hardware architecture, what we saw here. Regarding solving techniques, so we see here on the left side there are quite underrepresentation of the meta-heuristics. So this is a little bit contrary to the trend in a generic search-based software engineering. So there we have a meta-heuristics as the most popular ones, but here we don't have them. So we here in Industry 4.0 we usually meet exact techniques like ILP, interlinear programming. Maybe one explanation would be the maturity level of the Industry 4.0. So it's quite new compared to generic software engineering domains. So maybe that's one explanation why we have exact. So it's maybe easier to use out of the box ILP solution than to deal with the parameter tuning of meta heuristics like simulated annealing. So it's easier to use maybe ILP. And here we try to correlate solving techniques with the decisions. So it's not quite easy, but what we notice is that ontologies are most often applied with the matching techniques. This is also aligned with what we do in project and some other projects in basis. But so ontologies are quite often used for matching to describe capabilities, and constraint solving is often used for deployment and scheduling. And the last finding is what we try to see is how does the architectural synthesis optimization in Industry 4.0 differs to software engineering domains. So that's why we use the work from Alet et al. And try to compare the findings from this work with our findings. And this work focus on architecture optimization. So just trying to not just, but they focus on optimize. So they don't do synthesis of valid architectures. So they always have some optimization criteria there. So that's why we also extract from our works those optimization approaches and try to compare them. So what we see here is that timing constraint is quite important in Industry 4.0, which was to expect because real-time capabilities are the most important in industrial automation domain. So every second work was dealing with timing constraints. When we speak about the optimization, we see that in Industry 4.0 we have a mostly single objective optimization, and in this work of Alet et al. We meet often also multi-objective optimization. And regarding techniques that I already mentioned, meta heuristics, as I said, in software engineering quite popular, but in industrial automation not as much. And because I'm out of time, I'll just come to the conclusion. So just to sum up, this taxonomy of architectural synthesis evolves around three major subtopics, as I already mentioned. So architectural models, design space exploration, including design decisions, and optimization tools that we can use to perform this. And this taxonomy that we developed, we think that it can be used as a high-level common ground for communication, but also as an initial guideline to find the appropriate approaches to compare possibilities and to position own research work. And the last slide is also about research trends that I already mentioned and gaps. So I will not maybe go now once again through this because I just spoke about that. And that will be all. Thank you very much for your attention.